It's time. We can wait 1 minute more.
Okay, so now it's live streamed and
Oh, yes, we are now 51%. Maybe we can start. Okay? Are you ready?
yes, we already live. Yes.
Okay. Okay. Hello, everybody. We're happy to start our seminar. Today, the speaker is Professor Misao Sasaki Sensei. So he will tell us about perspective on inflationary cosmology. Please, 1 hour.
Okay, thank you. Thank you for the introduction. Well, so today I will sort of give kind of an overview of what I've been thinking about. So it's not really, something which is very new or very detailed, but so I hope you enjoy it. Anyway, and I guess maybe my view may be quite sort of non-common from standard sort of notion of inflation. But anyway, let me start. So first of all, what is inflation? Well, there are, many people talk about, and the inflation, the name of inflation, of course, is thanks to goods, but there are many, pioneers and also many, stories about inflation. Anyway, in the simple words, inflation, as all of you probably know, that is a quasi-exponential expansion of the universe, and it's very early stage. Hopefully, maybe around 10 to the minus 36, 35. I mean, it doesn't have to be that early, but anyway, that's the probably the time scale of our interest. So it's really very early time. And originally, as again, many of you know that it was meant to solve the initial condition problem of the Big Bang cosmology, that is a singularity and horizon flatness and so on and so forth. Now, after all, if any of them can be said to be solved, sort of depends on the precise definition of the problems, and so it sort of depends on who you ask. Somebody said it was solved by inflation. Somebody said no. So this is a bit kind of controversial point. But most important point of inflation is actually this discovery of these quantum vacuum fluctuations, which can give rise to all the inhomogeneous structure of the universe. So this is the most important prediction of inflation. And in some sense, all the sort of structures or organization or whatever we see in the universe, including us, are supposed to come from those quantum vacuum fluctuations. And recently, as many of you know, that now there's also a great interest in this gravitational wave background, and we think that if you have some quantum vacuum fluctuation, some fields, some matter fields, then gravity should be quantized. And if the gravity is quantized, then you also see a quantum vacuum fluctuation of gravitational waves or gravitons, and we sort of hoping to detect those gravitational waves from inflation. Anyway, so by the way, if you have any questions, perhaps I maybe it's difficult to detect these raise hands and so on and so forth. So just please scream, just interrupt me. Then I will stop and listen to your questions. Okay. All right. So well, this is the sort of standard picture that somehow inflation began, and then but it is controlled by some scale field, and the scale field is slowly rolling down its potential, and then in the end it goes down to its minimum, and then there we call it inflaton. The inflaton field start oscillates and reheat the universe. So although we call it the reheating, probably that's the first time universe was heated, and all this vacuum energy or the potential energy of the scalar field is turned into a radiation or in any relativistic particles energy, and this is the beginning of hot Big Bang universe. So, however, of course, we don't really know how this reheating process proceeds, and it all depends on what kind of model of inflation you consider. And so this is another one important thing that which we at the moment don't know how to say prove this stage of the end of inflation, but there are several ideas. Anyway, so this is one of a very interesting topics of inflation. Okay, so let me just discuss a bit more about inflation. Well, many people think that the inflation sort of results in homogeneous and isotopic universe, but that's not really true from a, let's say, semi-rigorous point of view. It's a assumption. It's not a consequence of inflation, and which is quite clear even from this famous paper by Guth, when he talks about solving the horizon problem and so on and so forth. He assumes a homogeneous isotropy background, and unless you assume homogeneous isotropy, you cannot actually discuss causality in how to say a precise manner. So in fact, it's the assumption, and most important assumption. Another thing is that so this is still not exactly solved, but now many people talk about modified gravity or many different type of gravitational theories, especially in the early universe, and they talk about the inflationary universe based on some particular models of gravity and so on and so forth. Or in those cases, it quite happens that there exist many different sort of frames, especially due to some conformal transformation degrees of freedom. Now, these days, people talk about disformal transformation as well, but in any case, there are different sort of a metric frames, and that in many of those modified gravity theories, these frames are not unique. So if frames are not unique, it's a bit how to say ambiguous to say in which sense you should call inflation. Because, for example, even if the inflationary universe, if space-time, I mean space is a spatially flat, then as we all know, and homogeneous isotopic. This is the standard flat Friedman, Lemaitre-Lawson, Walker metric. In this case, you can use the conformal time to scale out all the scale factor. Then the remaining part is just static Minkowski space. So by doing this conformal transformation, you can kill inflation. At the moment, my sort of a quasi a rigorous definition of inflation would be to probably depends on the existence of Einstein frame. And if there exists so-called Einstein frame where the gravitational part of the action is pure Einstein or Einstein-Hilbert, then if inflation occurs in that frame, maybe we can call it. That's the inflation. But this again, it is not settled yet. I mean, it also this is one of the confusing part of the recent trend of inflation. Anyway, assuming that you have some well-defined a notion of inflation, then the so-called horizon problem needs to solve a horizon problem. We think we need about 50 to 60 volts at least of inflation, and so this is related to the of course the energy scale of inflation, but in those relatively high energy scale inflation where the energy density is energy of the energy scale of the energy density is like 10 to 15 GeV or so. In those cases, we do need 50 to 60 volts. I will show you this kind of space-time diagram a bit later. But anyway, another thing is that this is just like the case of Big Bang cosmology, where once you assume thermal equilibrium as an initial state of the universe, then you don't care what kind of universe it was before this thermal equilibrium stage. And similar to the case of inflation, once you assume that the inflation lasted long enough, then we don't care, or we actually don't have any way to probe the physics behind beyond before inflation. So that's a good part because in this sense, you have some fairly well-defined predictions, but bad because once you sort of solve maybe all the say issues of inflation and you want to go beyond the inflation, then the inflation itself doesn't tell you anything about how to go beyond. It's exactly like the case of Big Bang, hot Big Bang universe. Hot Big Bang universe doesn't tell you how to go beyond that. And the inflation invented solve this Big Bang universe issues, and so far it became so successful. But this is the current situation anyway. Okay. Now, let me then briefly talk about the space-time diagram, or time-space diagram. So the horizontal axis is the log of scale factor, which is number of E-fold. Vertical axis is log of length scale, and then in this is time space or space time diagram, the so-called co-moving scale will be just a straight line with some angle. It depends on how you measure the length. But anyway, these a straight lines are the lines of the constant moving scale, or the maybe the this is how the expansion universe is following. Anyway, and then if you draw the so-called Hubble radius, it's the expansion rate inverse of the expansion rate, which essentially determines the local causal horizon scale, causal region. Then during inflation, as we know that this h is almost constant, therefore the co-moving scales go out of the horizon, Hubble horizon. But after inflation, universe probably is radiation dominated or matter dominated, whatever, but then universe becomes decelerated. In this case, this a co-moving scale now comes into the Hubble horizon, and this is how you solve so-called horizon problem, because as we from clear from this figure, if universe was decelerated all the way to the initial singularity, then all these scales, moving scale, would soon, if you go back in time, soon go out of the Hubble radius, which means that you cannot have all this, any causal sort of relations on those scales much greater than the Hubble scale. However, if there was an inflation, this co-moving scale eventually goes into the Hubble horizon radius, which means that in the early universe, they were connected causally, and you can prepare some causal physics to explain the large-scale structure of the universe today. And this is how we sort of solve the horizon problem. But again, as I said, this doesn't mean that this guarantees solves the homogeneous and isotropy problem. It just, in some sense, solves the horizon problem for the initial condition of the perturbations. So that's the most important part of inflation anyway. As it is written here, by the way, so if we assume some energy scale of inflation to be, say, 10 to 15 GeV or so, then a Hubble scale during inflation is about 10 to 10 GeV. That's the kind of typical models. But of course, this can be much lower than 10 GeV. And you may consider some low energy scale inflation. In that case, this, in some sense, this green line, the horizontal line, goes up because it becomes large, which means actually the number of efforts necessary to explain all these source of large scale structure fluctuations becomes smaller. So it could be as small as like 40 or maybe 35, 30. But anyway, in the standard case, we require this to be about 60, 50 or 60 number of efforts. Okay, right. Now, one thing which from the large case, not just homogeneous structure, but one important sort of a kind of a, you can call it prediction, but the result of inflation is that apparently our universe, current universe, it seems to have very, very small spatial curvature. And so we are living in a very flat universe. And this can be explained, or probably can, the only way to explain this is the inflation. So this is, again, I'm talking about the homogeneous isotropic universe, but in that case, you may have some open closed universe and so on, so with some non-trivial curvature. But if the inflation lasted long enough and reheated the universe, then it can happen that the part of our universe is only a very, very small portion of the very large, gigantic universe. And in that case, space will look like flat. Actually, if inflation is pure dojita, and if it just continues forever, then it's not just spatially flat, but it's everything would be essentially very flat. This is dojita invariance, and locally, if you go to a very, very small scale of the universe, then it's exactly the same as it has the same symmetry as the Minkowski, the Poincare symmetry. So so in that case, you have the real space-time flatness. But in some sense, fortunately, we think that we have some scalar field or something which breaks this invariance, boost invariance, and then you have some special frame. Existence of this special frame, say how do you call it, rest frame, is very important in cosmology to determine homogeneous and isotropy of the spatial section of the universe. And also on top of this, you have some fluctuations. And so that's kind of a quick review of inflation so far. Any question, comments? It's okay. All right. So
No,
okay,
I
let
think
me
it's
just
okay.
then go. Yes,
Yeah, I think it's okay.
is that okay? Right. So let's go to the dynamics of those perturbations. As many of you already know, that well, essentially we think they come from vacuum fluctuation. And here, this is the simplest picture of maybe I should say single field inflation model, slow inflation models. In this case, essentially because the potential should be sufficiently flat. At the leading order approximation, you can ignore the curvature of the potential. then they assume this inflaton potential to be essentially massless. Then then if you take the fluctuations, you get these equations for the fluctuations, where this 3h is the friction term due to the expansion of the universe. When the universe expands, of course, that if you have some pressure, then pressure works against the expansion and you lose some energy. That's why you have this 3h. 3 comes from the dimensions of the space. And omega square is essentially, if this massless, is just given by the comoving wave number k squared divided by a scale factor a squared. Now, this is if the k over a is very large, much larger than Hubble scale h, then essentially this is damped oscillation, and you have a oscillatory a scalar field, a vacuum fluctuations, but they just expand, and as universe expand, the amplitude becomes smaller and smaller and smaller. And if this sort of happens in the standard universe, essentially this never ends, and so the delta phi scalar field, the amplitude essentially becomes smaller and smaller and smaller. However, during inflation, because h is almost constant and omega decreases very rapidly, this sort of overdamp, which is the underdamped system goes overdamped, or the so friction dominated. So here's some sort of picture I draw, which is not so good. In beginning, you have this sort of a damped oscillation, but in the end, because the potential, effective potential, which is given by omega square, becomes 0. So then due to friction, this fluctuation just stops to oscillate. And the final value will be constant. And this means that the on scales much greater than the horizon, you have some non-trivial finite value of the delta phi, and which is the source of all the fluctuations of the universe. And as we all know, well, by the way, you know, we had a very sad news some time ago that Alexei Stravinsky died, but yeah, he is the first to derive these equations for the tensor perturbation, and tensor perturbation actually follows this exactly the same equations, and that's where we may be able to see. That's the reason why we may be able to see some vacuum fluctuation of gravity as well. Okay, going back to the scalar so-called curvature perturbation. So this just gives rise to some fluctuation in the scalar field, which is frozen on supervised scale, but it doesn't give rise to any, let's say, a source for the structure formation unless inflation ends. And end of inflation is very important. The point is, so this is the picture of space and again time. Now, and this blue horizontal lines, or the red horizontal sort of curve, they represent some spatial section or the hypersurface of the universe. And in the beginning, when you consider those quantum vacuum fluctuations, essentially you are computing these fluctuations in so-called flat slicing, or the slicing where the spatial curvature is 0. In this case, you can minimize the effect of gravity, and you can essentially compute those fluctuations as if you all these fluctuations in a flat space. Of course, this is an approximation, but we know this is a very good approximation. However, if when those scale fluctuations is freeze out, and then it becomes scale to become much greater than horizon scale, locally only thing you see is just some value of scalar field, and the physics must be determined by those value of scalar field, nothing else. So this means if the inflation ends, let's say after the scale field value arrived at certain critical value, then end of inflation is controlled by the surface where the scale field value is constant or homogeneous. And this is sort of illustrated here by this red curved hypersurface. So if you consider this hypersurface where the scale field is constant, homogeneous, then as it is clear from this sort of picture that you will have some non-trivial curvature of the space. And this is the source of the curvature perturbation. So in this sense, actually, of course, you can always solve the equation in this so-called the delta phi equals 0 slice from the beginning. But during inflation, it doesn't mean much. There's not really a meaning of, I mean, it's sort of a, it just choice of gauge, arbitrary choice of gauge. You can, there's no natural or how to say, a beta frame or anything during inflation. But as soon as the inflation ends, there appears some preferred frame where you're sort of how to say, rest frame of the universe is defined, and on which the temperature of the universe is essentially the same everywhere, because local physics is independent of global sort of inhomogeneity, anything. Just locally everything is determined. So in this way, as soon as the universe is reheated and become a radiation dominated, let's say, universe, then you have this inhomogeneities in the curvature. So this is and this is a essence, in some sense, essence of generation of the curvature perturbation, which is again not this is not always the understanding of many people, but I think this is very important. The most important point is that how the inflation ends, and that determines everything. You can solve the perturbation equation during inflation, that's okay, but it doesn't tell you how big the curvature perturbation would be in the end. The all very important things that how the inflation ends. Okay. Now, again, if recall this generic predictions of inflation or slow roll inflation in this case, as I said, you expect the universe to be very spatially flat, and then because of the almost a constant Hubble scale, and if you assume some physics vacuum is here, then for each, if you forget about this later stage, for each comoving scale, everything is essentially physics governing this comoving scale is the same as the physics governing on some slightly larger k, which means that the fluctuations, if there's some fluctuations, then fluctuations should be almost scaling value. And if there's a single field which determines all the evolution of the universe, then by definition, the fluctuation should be adiabatic. Gaussian, because if it is just the vacuum fluctuations, then if you have the direct a conversion of those fluctuations into curvature perturbation, like written here, then it's a Gaussian. So you will expect almost scaling value adiabatic Gaussian primordial fluctuation, and that will gives rise to the structure of the universe. And as we all know that this is perfectly consistent with the all the large-scale cosmological observations. And as they keep saying that at the same time you expect the almost scale invariant Gaussian primary tensor perturbations, and we hope to detect them in the future, in near future. Anyway, so these are kind of a more quantitative predictions. Then about the amplitude of curvature perturbations, this is the formula Milhanov and actually I derived. And there's some power spectrum index formula, which is given in terms of the first and second derivative potential. And there is this so-called consistency relations between the a spectrum tilt of the tensor perturbation with the ratio of the tensor to scalar ratio R. So if we can actually detect if the amplitude of tensor perturbation is large enough to detect this spectral slope, then we may be able to actually prove what is proved, this, say, simplest model inflation. Now, let me just talk about some about the observational result as probably quickly go through. The most recent one, of course, is the given by Planck. And as we all know that Planck spectrum TE is the polarization spectrum, temperature, a polarization correlation function, and E is the E polarization spectrum. All this the spectrum seems to be perfectly consistent with the some simplest model of inflation where the parameters is simply the amplitude and the power law index. And so so it's really amazing that they are and of course because we do need some dark matter and also the baryons and so on and so forth. Altogether, we have about 6 a degrees of freedom of to describe the model, but within just 6 parameters, it's amazing that all these data can be fit. Anyway, so the result essentially is that the amplitude of curvature perturbation seems to be about -5, 10 to -5. And if we simply assume the standard sort of those model of inflation with slow roll, then this indicate the vacuum energy to be as large as 10 to 16 GeV. Of course, it may be much smaller, but this is kind of a prototype or the typical value of the energy density. For the power spectrum, there's this Planck, the result gives you a very, very accurate spectrum index, which is minus 0.0355 means that slightly red tilted means that the amplitude of curvature perturbation becomes larger and larger on large scale. And this is consistent with some typical slow roll model again. By the way, so the fact that this is negative, and if you assume this ns minus 1 is negative to a very, very, very high large scales, exponential large scales, then this means that on those exponential large scales, universe is highly chaotic. So actually this tells you, so inflation is nothing to do with the homogeneous isotropy. Inflation can actually predict highly chaotic, universe, non-inhomogeneous universe on extremely large scales. So it's sort of how say, a, lucky that we are towards near the end of inflation and towards the near this last 50 and 60 fold where the amplitude of fluctuation is small enough, and so the universe is approximately homogeneous isotropic. As for the tensor perturbations, in the 10 years, 15 years ago, that we hoped that this would be large enough so that we could detect, but Now it turns out this ratio is less than 0.1 or almost 0.01 level, so it's becoming more and more difficult, but still we hope that this can be measured in near future. And this is what we have, kind of summary picture. The horizontal axis, the spectrum tilt, and this, which is apparently less than 1, so it's red tilted, and the vertical axis, the tensor scale ratio, which is very small, almost about 0.01, if you just take nominal sort of values from this data. Anyway, so this means that the most of the simplest model, for example, the phi-square model is apparently excluded. This is the curve on the top excluded. This region is the I think 97% confidence level or something, and it's much away from this. So we cannot really explain the inflation by simple model potential. Interestingly, the model which sort of fits all these data is so-called the R-square inflation, or the Stravinsky inflation, and which was proposed even before the terminology inflation was invented. But anyway, so this means that something, and R-square inflation definitely is non a Einstein, which means it's sort of a non-canonical in some sense as well. So again, of course, the most important message is that the inflation is the origin of all the structures that in the universe. However, there are some interesting sort of so anomalies, let's say. So those first spectra, as far as the spectral index is concerned, this is okay, and it is consistent with most of the standard model of inflation. But the fact that tensor scale ratio is less than 0.1 means that the energy scale of inflation is less than 10 to 16 GeV. And if it is too much less, then we would never see these tensor fluctuations, unfortunately. We hope that the energy scale inflation is at most like 10 to 15 GeV. Anyway, simple canonical models are almost excluded. Well, maybe I shouldn't say almost, it's essentially excluded. R-square model seems to fit best, but we don't know, because in this model, actually, you just simply assume there's an R-square correction, but no further higher order corrections at all. And you may have some interesting model to explain this. But anyway, definitely this is non-Einstein theory. So either you need some modified gravity, or maybe the interaction, the corrections, R-square type corrections to Einstein gravity due to some vacuum quantum theories stops there, and no higher order comes in, and so on and so forth. FNR, this is a so-called the non-Gaussian parameter, and as I said, that the most important prediction of the standard slow inflation is that the Gaussian, it's the pure Gaussianity, or this FNL parameter is much less than 1. So if you have some small non-Gaussianity, which is finite non-Gaussianity in the observations, then we will be sure that something non-canonical is happening. But anyway, so it's interesting to find some, or they look for some models which can explain those non-canonicality. Therefore, let's just consider some of the standard, beyond standard model inflation. And there are many sort of, how to say, proposals. One is maybe the canonical, kinetic term is non-canonical. In that case, you may have some non-trivial sound velocity. And in this case, there's some special kind of Gaussianity, which is not the what is sort of what we call local Gaussianity, which is most easily constrained, which is constrained to be order 1 or less. You may have some different once as soon as you consider non-Gaussianity has infinite degrees of freedom. So you have to sort of specify which type of non-Gaussianity first. At least as far as this so-called equilateral type in the Fourier space, it represents kind of triangle diagram. But anyway, they are supposed to be proportional to 1 over CS squared. Planck tells us that this CS cannot be so small. It is about 0.02, greater than 0.02, and so on and so forth. Maybe you have non-minimal coupling to gravity, like one of the most famous model is that so-called Higgs inflation, where you assume that Higgs actually plays the role of inflaton, but you do need some this non-minimal coupling. And so there is some relation between the this non-minimal coupling with this tensor to scale ratio, given the amplitude with curvature perturbation, and so Planck tells us that this non-minimal coupling parameter is at least 10 or greater, which means it looks like a very sort of a non-trivial large coupling constant. From the point of view of a coupling constant, if z is much greater than 1, it means something highly nonlinear is going on.
Oh,
You may have
excuse
some.
me. Oh,
Yes.
excuse me. May I interrupt you? I
Oh,
see
sure, yeah.
that there are 2 people who would like to
Oh,
ask
yeah, okay,
question.
yeah. Just,
Okay,
yes,
is okay
please.
for you now?
Oh, yeah, sure,
First
please.
is Igor Volodь. Igor, please ask your question.
Go ahead,
Let
please.
me ask the following. Is it okay to say the Stravinsky model fits well with experiment?
Is it okay to say what?
That the Stravinsky model fits
Yeah.
well with observations?
Yeah. The Stravinsky model is at least, as far as I know, the best fit model. Yes.
Okay, now I have the question about Stravinsky model.
Yeah.
You stress that we need to discuss vacuum fluctuations.
Yeah.
Okay, so we need quantum Stravinsky model.
Yeah.
But Stravinsky model is equivalent to Einstein plus exponential scalar field. So it's non-renormalizable. Okay?
Well,
What do you do with this?
Well, we were not sort of how to say dealing with any model we're dealing with in that sense is non-renormalizable, because as soon as you include gravity, we don't know the full theory, right? So in that sense, it's all kind of effective theory, assuming that the some cutoff scales is much greater than the scale of our interest. So we do not discuss a non-renormalizability at all.
But vacuum fluctuation, you consider vacuum
No.
fluctuation.
If you just take the leading order vacuum fluctuation, it's Gaussian and doesn't contain any. If you do not go into loop contribution and so on and so forth, then everything's okay, right? Essentially, it's a free field theory.
Sorry, Misao, I think you can include that you can embed Starobinsky in a renormalizable theory if you add the Weil square term, right? And you will not have any high order term that needs to be taken into account.
It seems you have to
No. The whole point is that once you go to the Einstein frame, you do need highly non-trivial potential, which is exponential pi or something.
No, sure. What I mean is that if you start from Jordan frame R plus R square and you add Weil square, in that case we will have a renormalizable theory. You can still go to Einstein frame.
No. So then you have you're talking about two-field model.
No, just like.
I mean, sorry. The Stravinsky model is pure R square, right?
No,
R plus R square.
I understand. So
there's no scalar field in the so-called Jordan frame.
Sure,
Okay?
but you have an extra degree of freedom, which is a scalar. degree of freedom.
You have to add
So
each
then
square.
you can also, you know, introduce the scalar degrees of freedom in the Jordan frame, but in Jordan frame, it's not, say, canonical in that sense.
No, I understand. No, I was referring to the comment larger square correction, but the negligible high order terms must. So this is a problem if you have a non-renormalizable theory, so you need to take into account high order correction.
Oh, yeah. Well, okay. So maybe I shouldn't say this. What I'm just saying is that we don't really know this, why the Stravinsky works well. And then maybe there's some deep reason behind, or maybe it's just by chance, and there's some real, say, true theory, which is completely different to Stravinsky's model.
Mhm.
We don't know. But
No, I
what,
think,
what I'm just saying is that for the moment, this model seems to work best.
No, I think I appreciate that because I think Stravinsky can be embedded in a renormalizable theory if you add something more in the Lagrangian, like a Bile square term.
Well, that
that's,
I don't know really much about those, you know, how to actually make this model work. And maybe there are some way, maybe there aren't. I don't really know. And in some sense, I don't care at the moment because that's not really an issue. Okay.
Okay.
No, the
Okay.
problem with y square that it leads to ghost.
Sorry.
If you add y square, it leads to ghost.
Yeah, but I think
Oh,
there
yeah,
are
that's
ways-
right. That's right.
Yeah.
So once you have some ghost, then you have to know what it means. I mean, if
sure.
You just simply count the degrees of freedom, you have to deal with ghost. But there are some
Some people doing
again
something.
proposals.
Yeah.
For example, and a way to kill this ghost degrees of freedom, and it is sort of related to the this meaning of this why the R square can gives rise to scalar degrees of freedom. This is if you assume this this is a correction and this gives rise to this degrees of freedom, then you have to deal with ghost because, but if this you don't assume that there would be no new degrees of freedom. It's just some small quantum corrections which in the end should be non-perturbatively computed. Then actually we shouldn't have any new degrees of freedom. So so in that case, this R squared sort of dies because we have no degrees of freedom. But anyway, so it's at the moment we don't really know, and then since we don't know the say real theory or true theory of gravity or something, for the moment everything is kind of effective. Okay. And we have to sort of live with it. I mean, unless you know some
Excuse me,
theory.
there is one more question. There is a
Mhm.
question from Shravan. Shravan,
I'm-
could you please ask your question?
It's a
Okay.
maybe a comment or question, I don't know. So the thing is about non-canonical models, there is a sound speed and we need to restrain the sound speed to be between 0 and 1. So this is extra fine tuning. So all the models with non-canonical kinetic terms. So do you think they are natural?
What do you mean by natural?
I mean, we have to do extra fine tuning, which is kind of artificial thing. We need to control the dynamics so that sound speed is not superluminal.
No. So again, this is I mean this. Well, yeah, you know, some sort of has a top-down theorists always talk about this fine-tuning things, but again, in a cosmology, in some sense, you know, we build up things from bottom. Especially, you know, we very much rely on, say, observations. And for example, we know that from this Planck observations, we have, for example, the curvature parameter amplitude 10⁻5, which is a fine tuning, of course. Yes, ns-1 is 0.035. That's fine tuning.
Yes,
So
but then
we need fine tuning because its observation tells you to, you know, have to make your model consistent with the observations, right?
Yeah,
The same thing. So you know, observations is most important in cosmology, and then of course theorists must think what kind of a fundamental theory it should be, you know, explained, all these things. But at the moment, what we know or what we can do to to test or to say think of some effective model of inflation, and that can explain all these things and yet have some interesting predictions, which can be tested. And once we test it, and once it happened to be like in the case of Stravinsky model, it happened to be completely consistent with observations, then you have to think about what kind of theory behind. Yes. So that's the kind of attitude towards,
Okay.
say, final theory, let's say.
Yeah.
Okay. Is that okay?
Yeah, it's fine. Thank you.
Yeah. All right. So I don't know. How many more minutes do I have?
About 10 minutes.
10 minutes, huh? So, okay, so let me just go quickly. So there are some so-called anomalies on a very large scale, which might be a hint beyond say inflation. And many people talk of many things, and there are some interesting sort of things is that maybe this is due to so-called the string landscape things, and so there are many kind of models or theories, but let me just skip. The recent sort of more interest is going on to the small scale, because now different from large scale means a scale much greater than, say, horizon scale. The small scale is definitely within our causal horizon. So if we have some means to detect something, and then we may be able to probe this early universe, and this what we think we can do at the moment is using gravity, because gravitational wave or anything can actually penetrate until today without interfered by many sort of physics between the early universe and the current universe. And so and besides, since there are so many constraints on the amplitude or nature of the perturbations, the people's interests are now shifting to the small scale, and especially on small scales, we may be able to see some fairly large amplitude of the gravitational wave perturbations, and that can be detected by various ways of means of the detectors. So here, for those people who know cosmology or observational cosmology, what I'm saying is that it's 1 gigaparsec, 10 to 9 parsec is the horizon scale, while small scale, I mean about 1 parsec. So it's about 9 order of magnitude smaller than what we call a large scale structure. And so this is really a small scale. Yes. Oh, we have some questions in the chat, or I don't know. Is that okay?
It's okay.
Nice, okay, it's okay.
Okay. Oops. No. No, I have. Oh, wait.
Sorry,
Okay.
sorry, it was me. I was meant for a particular person, so it was in Italian. Sorry.
Oh, okay. Yeah. Anyway, so one of such is that if, let's say, so for something interesting to happen, of course, first of all, in many cases we think that some amplitude of those curvature perturbations should be large enough to be interesting, much larger than 10 to minus 5, because 10 to minus 5 is too small to be interesting. Now, we want to have some if we want to have some interesting scales, it must be at least 10 to minus 2 or 10 to minus, even 10 to minus 1 or so, 0.1. And so, oops, the one of the interesting prediction is that if you have some very large amplitude fluctuations, then I mean, if a large amplitude in the large power spectrum. Power spectrum is essentially the how do you call it? A dispersion of the Gaussian distribution, probability distribution function. So that's the mean value of fluctuation. But of course, any probability distribution have some tails where the amplitude of fluctuation is very large, although the chances of having such large fluctuations is very small. But even if it is very small, if you have very large fluctuations, it can give rise to very interesting structures. One of the those structures are so-called primary black holes. And here's this essence of the how the primary black hole form. So if you have some fairly large amplitude fluctuations, but in the beginning it's on sort of called the super Hubble scales. So this red arrow represents the scale of a Hubble size, and blue arrows represent the size of the perturbation scale. So in the beginning, it's nothing. There's nothing. I mean, because it's the super Hubble scale, nothing can happen. But as the universe evolves, the Hubble scale expands relative to the comoving scale, and eventually the Hubble scale becomes equal to this comoving zone fluctuations. At that moment, if the amplitude of the curvature perturbation is over 1, then they form a black hole. And this is just like a real, when in undergrad sort of the courses, we learn 3 different kinds of cosmology: the open, flat, and closed universe. And if you have the closed radiation dominated universe expands and stop at certain moment because of the positive curvature. Positive curvature term stops decelerate expansion and start to collapse. And essentially, this same thing happens in the early universe. If you have the positive curvature region, which was amplitude rising up, that effectively behaves like a closed universe, and then just collapse to a black hole. So this tells you essentially the mass of black hole is that horizon mass at the time of those collapse. And the equation is like this. So about the temperature of 100 MeV, it would be about 1 solar mass, which is an interesting scale because, and people talk about this these days because 100 MeV is the QCD phase transition scale. And so maybe there are some interesting black holes, primary black holes of all the solar mass. This scale corresponds to about 1 parsec in comoving lengths. And this is the current sort of a status of the constraints on primary black hole amount. Vertical axis is the fraction of primary black hole relative to the dark matter. So if it is 1, it means that total dark matter is totally occupied by primary black holes. Apparently, as you could see, that there is some regions. This is about in terms of solar mass 10 to minus 11, 12 to 10 to minus 15 solar mass, or approximately 10 to 20 gram or so. If primary black hole mass is like this mass, then there's essentially no constraint, and so there's a possibility that the black holes of this size can be the dark matter of the universe. And people are now considering how to actually prove or disprove such scenarios. On the right-hand side, you have this about 1 solar mass or 10 solar mass regions where we know that there are lots of binary black hole mergers are detected by LIGO and Virgo. And some of them actually could be primordial, and that's another interesting scale. Anyway, since I don't have much time, so let me just quickly go through the significance to the say gravitational waves.
Oh, excuse me, maybe you can spend, if you need, 10 minutes more,
Oh,
okay?
okay, thank you.
Don't,
Yeah.
don't.
All
don't-
right. Okay, thank you very
Okay,
much.
don't rush,
Okay.
please.
Yeah. Okay. Anyway, so the important thing is that, as I said, now in the beginning you have some fluctuations in the curvature of the space-time. This is the curvature perturbation, and most of the curvature perturbation's amplitude is, let's say, not so large. So as soon as they come inside the horizon, they behave like a sound wave and oscillates. But these oscillations at second order gives rise to gravitational wave. So this is called induced gravitational waves. While in some rare regions of the universe, the amplitude of perturbation is large enough that they form primal black hole. So this means actually the mass of the primal black hole, the size of primal black holes is a very, how to say, there's essentially one-to-one correspondence with the mass of primal black hole and frequency of gravitational wave. And as written here, if primal black holes are dark matter and the primal black holes of say 10 to 21 grams as a nominal value of the say black holes, then the corresponding gravitational wave frequency is 10 to minus 3 hertz, which is exactly in the so-called LISA band. And we hope that in near future, the LISA is the space interferometer, gravitational wave interferometer. If they fly, they would detect these gravitational waves. And then once they find this background cosmological gravitational waves, that's a very strong hint to that maybe the dark matter is totally primal black holes. Another interesting is, of course, this LIGO-VIGO black holes, which is about 10 solar mass scale, more or less. And then corresponding gravitational wave, induced gravitational wave frequencies like 10 to minus 8 hertz. So this is actually the interesting range for the so-called pulsar timing array experiments. And let me just quickly go through the current status. So the LISA has not still not flight yet, but hopefully within 10 years or so, and you will be able to have these detectors in space. And then what we have found here is that if you assume sufficiently good sensitivity of LISA, this is probably the design sensitivity. If this is achieved, then actually essentially independent of the possible non-Gaussianities of the initial curvature perturbations, seems that it's a very good chance that you would detect the gravitational waves if you assume a primary black hole, the dark matter of the universe. So in this sense, or vice versa, if we don't see those background that essentially kills this PBH equals CDM scenario. Now, just about already like 6-7 months ago, in all these pulsar timing array groups announced an interesting sort of evidence that they might find some evidence for the stochastic gravitational background. And it apparently the best fit model would be some induced gravitational wave, induced gravitational wave seems to be the best fit model for this result data analysis. However, in this case, it seems that the amplitude of curvature perturbation is very large, almost order of 0.1. And if you just simply assume some simple sort of a scenario of PBH formation, then it seems that this gives too many primary black holes, and therefore maybe there are some problems. Either the amplitude is too large, or maybe the amplitude of curvature perturbation may be okay, but this sort of how to say PBH formation sort of a criterion something wrong, or maybe the actually the curvature perturbation have some highly non-Gaussian features which can actually account for this correct amount of PBH and so on and so forth. Anyway, so the gravitational again, let me just stress this, that in small scales, of course, there are many other sort of sources of gravitational waves, but as far as the inflation is concerned, the direct evidence of some fluctuations from inflation is concerned, these primary black hole and induced gravitational waves those are always a very interesting sort of source of future physics, let's say near future physics, and which maybe if we are lucky enough, we will be able to find some evidence in, and maybe, as I said, this nanograph and other CPTA and other groups of the pulsar timing array groups, what they have found might be some indication of this early universe physics. Anyway, so let me just finish by I'll say listing some of the future issues. There's said, as I said in the very beginning, this is more or less kind of philosophical question, but how do we define inflation if there are so many different sort of frames you can think of? So what I have said is that maybe at least if you have some Einstein frame, that Einstein frame would be the frame where you define, or in a similar way, if we just take the perturbations, then essentially grab them, the tensor perturbations. If the tensor in the frame where tensor perturbation behave exactly the same as Einstein, then you may call it the quasi-Einstein frame. And then that in that frame, if the inflation happens, then we may call it inflation. Of course, we don't know anything about initial condition before inflation. As I said, the inflation cannot solve initial conditions of inflation. You have to go beyond the inflation. Maybe it's a multiverse or something else. We don't really know. That's an interesting issue. Reheating is another, well, this is more physical problem, and we don't really know how the universe reheated. And if there's any way to probe reheating process, that would be fantastic. Nobody knows at the moment. We have,
Okay,
I just
excuse me, Philippe had a question.
Yes.
Excuse to interrupt just now. Philippe,
Yeah,
do you
well,
want to
you're
ask a
muted,
question just
please,
now?
Philip. Please, you're muted. You have to unmute.
Oh, I'm sorry. No,
Unmute.
Yeah.
just wait for Misao to finish.
Oh,
Okay.
yeah. So may I finish then? Okay. Anyway,
Okay.
so as you could see that we may have some interesting nonlinear effect, especially on very small scales, and which related to primal black hole induced gravity and so on and so forth. So, and in the end, of course, a inflaton should be identified with something, and which is the probably most important but not so easy task. But apparently, we have so many interesting things, you know, from inflation, and now, you know, with this gravitational wave, astrophysics cosmology coming into reality, we have more tools to probe the early universe, and especially the physics of the inflation. So I could say this is kind of observational or experimental inflationary cosmology. Okay, let me finish this. Thank you.
Okay, very much. Thank you very much for your very instructive talk. You present a lot of materials. And please, Philip, ask your question.
Yes. Okay. First of all, thank you for this very nice presentation. I have a couple of questions, but let me just ask something very quickly about Starobinsky theory. Is the propagator for r plus r squared 1 over k squared plus 1 over k squared minus m squared, or 1 over k squared minus 1 over k squared minus m squared in the Starobinsky theory? In other words, is it r plus r squared or r minus r squared? Does it depend on
this in the standard sort of how to say a metric convention? It's r plus r square, which gives yeah.
Yes. So as that theory stands, and as Luca was pointing out, that one is not renormalizable. However, r minus r squared is renormalizable. And I think it was Igor raised the question about ghosts. Well, I have done a lot of work on that with Carl Bender, and it turns out you can change you're using the wrong inner product if you use the Dirac norm, the overlap of a state of a ket with its Hermitian conjugate. If you use the overlap of a ket with its CPT conjugate, then you have a positive norm theory. So, but that's a separate comment. But
You still need a Weil square. You need a Weil square anyway, Philip, right?
yes, what we would call R minus R squared. So you see, it's 1 over k squared minus 1 over k squared minus m squared, only goes like 1 over k to the 4 asymptotically. And that's why it's a renormalizable theory.
No, but the sign of the square only changes the sign of the mass square.
Oh,
You give
okay.
either a tangent or not. We not change the sign of the full propagator.
You need
You
need a little bit more.
Yeah. I mean, so there may be interesting sort of things to discuss, but if as soon as you put minus sign in front of R square, then it won't be a model for inflation. That's for sure.
That's what I was asking. Yes. Now let me go back to my key question. We have an idea that there is going to be a theory of quantum gravity whose low energy limit will be Einstein gravity. And therefore, most of cosmology, we can deal with classical Einstein gravity. However, if you want to go back right to the beginning, where you do have vacuum fluctuations in the inflaton, I don't see how you can pretend that you don't have to consider vacuum fluctuations in the gravitational field. And if you don't have a renormalizable theory, then they're going to be infinite. So it seems that the whole idea of pretending you can get away with without needing to know what quantum gravity is would not be true in the very, very early universe.
Probably you're right. Yeah. But since as you correctly described, since we don't really know the renormalizable or some correct theory of gravity, in some sense we are sort of ignoring gravitational part. We are just stop at the linear level of perturbation, and as far as the gravity is concerned, you just stop, and you can discuss some higher order corrections to matter sector, but you don't deal with gravitational part. And in this way, you sort of avoid issues. And that's what many people do in the so-called effective field theory approach. Yeah. Yes.
Okay. I see the questions from Alberto Salvio. Albert, please
Hi.
ask your question.
Yeah, it's a question regarding primordial black holes. As far as I know, people typically find the necessity of fine-tuning the parameters to have a large enough amount of primordial black holes. My question is whether you know some models where there's no fine-tuning and still you get copious production of primordial black holes.
No, I don't think so. I mean, this is essentially level of fine-tuning is slightly different, but essentially the same as all the other fine-tuning, like why the dark matter universe is about the same amount as the baryons and so on and so forth. Why the dark energy is just start to dominate the current universe. Coincidence problem, so-called. Everything is related. So from theoretical point of view, I don't think there's any natural solutions. You have to tune your parameters to fit observational data.
Okay, thank you.
Okay, I see a question from Gabriel Veneziana. Gabriel, hello, please
Yes.
ask your question.
Hello.
Yeah, can you hear me? Because
Yes.
Okay. Thank you, Misao. Was a very interesting talk. I just have probably missed it. I would like to understand better how you get these extra gravitational waves from the primordial black holes. Does it have to do with the collapse process itself, or
No. Yeah, well, of course, there are some gravitational waves from collapse process itself, but the main part is that assuming you have some, those curvature perturbations from inflation, then first forget about primordial black holes. Then when they comes inside the horizon, then they start to oscillate. This oscillation induces gravitational waves at second order.
So
Yes.
these are the
So-
normal modes, the quasi-normal.
Yeah, well, it's just, those curvature perturbations, essentially when they comes inside the Hubble horizon, they behaves like sound waves.
And
And
this can
sound
be,
wave means that you
yeah.
have some oscillations of matters, and those oscillations matter produce gravitational waves.
So you can reliably compute them if you.
Yeah. So this
you know
part
the
is
math.
quite reliable, and the black hole part is not reliable yet. But as I said, every once in a while you have some region of space where you happen to have some large fluctuations. This happens because you always have tail of perturbations, the probability distribution. So these large fluctuations can become black holes, and then they are rare events, but the mass is determined by the Hubble size. Therefore, this frequency of gravitational wave and the mass of black holes are correlated, very strongly correlated.
Okay.
That's why if you find primal black hole, you should find gravitational waves.
I see.
Okay.
May I add a small comment?
Yes.
Since I don't want to say wrong things when I give talks about inflation, do I understand correctly that you still agree that inflation can explain homogeneity and isotropy of our own patch, the patch where we live in? I mean, I don't care about
Well,
what
yeah,
beyond our
yeah.
horizon.
So again, sort of okay. Once you accept the amplitude of fluctuation 10⁻⁵, yes.
Yeah.
I mean, as I just said in the beginning, or somewhere here, I forgot. The NS is less than 1 means that the fluctuations are larger on the large scale. If the amplitude of fluctuations are about, let's say, 10⁻⁻1, then of course our universe could have been, well, maybe on the much smaller scale, you may have some Hubble patch where the universe looks homogeneous, but our current universe could be highly inhomogeneous. So it's all
On
because,
very large scales.
Yeah. So and a very large scale, there's no reason why this very large scale is not our scale. Yes?
I see.
It's only because the amplitude, we find that amplitude 10⁻⁵. That's the reason that at least our patch of the universe is homogeneous up to this 10⁻⁵ level.
Okay, because I usually present things slightly differently. Tell me whether it's wrong. I would have said that without quantum mechanics, inflation would give two homogeneous and two isotropic universe. So it will not give
Yeah.
structures.
Maybe
So
yes.
it is only when you add quantum mechanics to inflation that you start to be, slightly inhomogeneous.
Well, no. So yeah. So that's slightly is because of the observations.
Yes.
And in some sense, as soon as you add those quantum vacuum fluctuations, then universe can never be homogeneous and isotropic.
I agree.
Yeah.
You say that quantum mechanics could perhaps spoil the homogeneity.
That's right.
That you would get classically.
That's right.
Very good.
Yes.
Very good.
Yeah.
I agree.
Thank you.
Thank you.
Okay, I see a question from Alexander Zakharov. Sasha, please ask your question.
Okay, thank you very much. Do you hear me?
Yes.
Yes.
Okay, thank you very much. Misao, thank you very much for a very interesting talk. I have a question about primordial black holes and the opportunity to detect them with LISA. So problem with LISA will observe so many sources, different sources in different directions. So, and when we want to decompose this signal, so we have some uncertainties in location of this source and also parameters of this source. And could these uncertainties mimic existence of primordial black holes? Because problem is very difficult, it seems.
I understand. Yes, I think yes. That's a very difficult issue. I mean, especially if there are many different sort of backgrounds I mean, if there are only some in isolated sources, then if the signal to noise ratio is large enough, then we can sort of separate out, and then you find, just like the case of the original finding of CMB background, that the cosmic micro background, that if you get rid of all possible noises, all possible local sources, and then, you know, the remaining one was the background, cosmic background. So you probably have to do similar things, and hopefully, if this is the dominant background, and if it's the dominant isotropic background, then you may be able to detect or identify. But it's observationally, I think it's quite challenging. I think I agree.
Okay, thank you very much.
Okay, I see one more question from Igor Pavlovich. Igor, please ask your question.
Okay, thank you for a nice talk. I would like to ask about your opinion about the derivation of inflationary models from quantum cosmological models. You know, there are many research, the people try to derive inflation from, say, tunneling from nothing, boundary without boundary, so on. What is your opinion about this status?
Right. Yeah. Well, so the creation from nothing is sort of one of my favorite models, because in some sense it solves initial condition problem. But of course, you know, if we can actually prove, or maybe, you know, at least find some evidence for such a tunneling, is a different question, and hopefully. Yes, you know, now this is related to this large-scale anomalies. Maybe some of those large-scale anomalies are related to those tunneling events, and so if you have some interesting sort of model of the early universe before inflation, maybe there's a way. And one interesting sort of course, signature is that if actually it was a tunneling just before this inflation and it happened, and the number V for this just about 50 or 60, then actually we may see the non-trivial curvature, but this curvature should be negative. Current observation doesn't really have that accuracy, and it can be slightly negative, slightly positive. Most sort of best fit model tells you maybe it's slightly positive, but if it is positive curvature, then it may be another challenge to inflationary model. But anyway, if it is slightly negative, like the in terms of the omega minus omega k, the curvature contribution to the total density of the universe is 10 to minus 2, 0.1% level, then if this can be actually tested more precisely, and then and if you find it, then this is an evidence that our universe was born out of tunneling. Yes.
Okay, thank you.
Okay, I see one more question. There is a question from Sergei Vernov. Sergei, please ask your question.
So thank you for your interesting talk. I have a question about primordial black hole formations. For example, you can describe such formation in FATAR gravity models with scalar field. So you can explain such formations both in Jordan frame and Einstein frame. Is it equivalent ways?
Yeah. Well, I don't know other cases, but as far as the conformal transformation is concerned, then the definition of black hole essentially is a causal structure, and causal light cone structure will not sort of be altered by this conformal transformation. So I think if a black hole is defined in one frame, then it means that you have black hole in the other frame.
Yeah, the mass of black holes is invariant under conformal transformation.
Oh, no. You're talking about the mass.
Yes.
Then here, yes, I'm just simply assuming standard cosmology in Einstein universe, Einstein frame, Einstein theory. If you have some other theories, maybe you have some slightly different sort of mass and so on and so forth. But since those black holes, when of our interest, as you could say, forms of the temperature which is not so high, maybe 1 GeV or something. Or maybe 100 GeV, like a electric weak scale. That's the approximate scales where you can get some fairly small cold dark matter black holes. Anyway, so a energy scale is not so extremely large, and therefore we think more or less Einstein theory is a very good approximation to if there's any modification to Einstein, but this modification should be small enough around that energy scale. But of course, it may have some completely different theory. In that case, maybe a mass of black hole can be quite different from what we expect. Yeah, I haven't thought about it yet, so I cannot really answer your question, but that's my expectation.
No, thank you.
Okay, more questions, please? If there is no more questions, let me ask a general questions. Suppose you have unlimited funding. What experiment you can try to organize to get more information about inflation, primordial black hole, gravitational wave? So what would be more interesting from your point of view? What we can
The
in
question is
principle
what kind of
realize?
experiment would be interesting?
Yes.
Yeah, it's a difficult question because cosmology is you sort of rely on the sources which you cannot produce on Earth, and so you sort of have to assume there are some interesting sources. For example, one interesting thing about this primary black hole, as I said, this sort of 10 to 20 gram or so, this range cannot be observed by, let's say, standard gravitational lensing because the size is smaller than the wavelengths of light. But if you use the gamma ray, then gamma ray can have some gravitational lensing effect if you have sufficiently compact source of gamma ray. Unfortunately, so far we don't have any such sources in the universe. But if we find in the future or near future, all of these cosmological observations or maybe gamma ray observations, if we find really, really, a almost point like gamma ray sources in the universe, then maybe we can use that to detect the gravitational lensing of those gamma rays by those primordial black holes. So that's one thing I can think of, but it's not so easy. Yes.
I see. Thank you very much. So if there is no more question, let's thank the speaker again for very instructive, very interesting talk. Thank you very much.
Thank you.
Thank you very much, Misao.
Thank you.
All right.
Please send me your slides. I would be happy to
Oh, yeah,
upload
okay,
to our
okay.
website.
I will
Thank
send
you. Bye.
Thank you.
Yeah. Bye-bye. Thank you.
Bye-bye.
Bye-bye.
Thank you.
Bye.
Bye.
Alexei, please stay a few minutes. I would like to ask you some questions.
Okay. Sure.
Bye-bye.
Bye-bye.
Alex, don't forget to update the program.
Yes, I will update it
Okay.
now. Yeah.
Okay. See you next week, right? No, next week.
Next week.
Next week,
Yeah,
yes.
next week actually.
Okay.
By the way, Luca, one thing.
Ciao Alberto.